Welcome to a short introduction to the Nicomp Dynamic Light Scattering System. We can configure the Nicomp N3000 several ways. It could be configured just for particle size or for particle size and zeta potential. The optics can either be configured as a fixed 90-degree system or multi-angle goniometer, where we could measure the light scattering at essentially any angle. The light source could either be a standard laser, or we could add high-powered red or green lasers, depending on the interaction of light with individual samples. For a detector, we can use a PMT or an avalanche photodiode detector to have the highest sensitivity to small particles and very low concentrations. Some unique features to the Nicomp include being able to do automatic dilution of samples, being able to integrate to an XY autosampler. You see here an autosampler capable of measuring up to 90 samples automatically, and also some unique capabilities to do online size measurements using dynamic light scattering. Taking a measurement is very easy with the Nicomp. We simply prepare the sample, which is sometimes simple, sometimes a little more complicated, but we won't cover that today. We place the cuvette in the system, and looking at the setup screen on the right, we could either leave everything in automatic in terms of baseline Nicomp parameters and also choosing the neutral density filter, or we could interact with this and adjust this for specific applications. Once we've configured the system for the measurement, we hit go, we hit one button, we take a measurement, and we look at the results. A feature that is unique with the Nicomp is an immediate presentation of an error calculation, a chi-square error, which then indicates, do we think there's a single peak, or should we use the Nicomp algorithm to look for a multimodal result? And this ability to do multimodal analysis is one of the key strengths of the Nicomp DLS system. On this slide, I'm showing several results where we prepared bimodal samples of polystyrene latex standards. On the left, you see a sample that was a mixture of 100 and 170 nanometer polystyrene latex. If we measure using a Gaussian distribution model, we get a single mode, but then switching to the Nicomp algorithm, we actually split these peaks at 100 and at slightly larger than 170 nanometers. Only the Nicomp system has this kind of resolution to be able to split peaks that are this close to each other. The example on the right is showing similar results for samples that are at 150 and 200 nanometers. Down to the lower right, you see if we used a Gaussian distribution, it would merge it into a single peak, but when we applied the Nicomp algorithm, we split it into the two peaks at 150 and 200 nanometers. So this kind of resolution is unique to the Nicomp and is one of the reasons people prefer to use this when measuring complex samples. This slide actually shows our ability to resolve three separate peaks using the Nicomp algorithm. This is actually cholesterol in blood, and cholesterol has three components, HDL, LDL, and VLDL. This shows our ability to resolve these three peaks that are fairly close to each other and is a unique capability of the Nicomp DLS system. The system is also very sensitive to very small particles, particles under 10 nanometers. On this slide, we see three results. These are not measured together. These are three individual measurements plotted on a single graph. These were molecular assemblies where the monomer was at 1.7 nanometers, the dimer was at 2.9, and then the tetramer up here at 5.9. And the Nicomp very accurately shows these three different sizes right in the range where they're expected for this particular molecular assembly. This shows data from Buckminster fullerenes, or buckyballs, down here where the first peak is at 1.4 nanometers where they're expected. So we show the peak of the very small buckyballs, and up here are some agglomerates up at 200 nanometers. So this is showing the ability to both detect very small particles and also being able to resolve the second peak of the agglomerated sample. This system can be configured to be a multi-angle goniometer. The reason we would do this is typically when we're measuring larger particles. For very small particles, as everything is down under, say, 20 nanometers, the scattering is isotropic and the scattering is the same at all angles. But we're measuring larger samples, let's say it's a lipid emulsion at 300 or 400 nanometers, then we have not only the scattering dependence, which is d to the 6, diameter to the 6 power, but we need to take in this intensity form factor g squared. The data I'm going to show on this slide is a mixture of 90 and 300 nanometer polystyrene latex samples. We measure them at 90 degrees, and here closer to backscatter at 158 degrees. you see the size distribution, and then the black line is this plot of g squared, which helps us understand the form factor. As you see in the upper result, the form factor has a minima at 500 here. And when you hit a minima with the intensity form factor, then there could be an error in the calculation of the size distribution, especially when we're converting it to a volume distribution. What you see at 90 degrees, the form factor hits here, and we get a very accurate result. We know that this mixture is about 10% by volume of 300 nanometer PSL. But when we measure in the backscatter direction, we actually see there is a minima right here where we're trying to measure the particles, and this creates a large error in attributing the correct volume percent at 300 nanometers. So this is the kind of sample where there's a lot of benefit by having a goniometer, and just measuring always in backscatter is not the best way to measure every single sample. We can also measure many samples if you have a high sample throughput. The auto sampler can measure up to 90 samples loaded in a tray, program the system, walk away, and get all of the results. Another unique capability of particle sizing systems is the ability to do dynamic light scattering online or at line. Here we take the sample into a variable diluter. The sample comes in, we dilute the sample, bring it into the cell where we take the measurement, stop the flow, take the measurement, clean up, and do another measurement. This is useful when dealing with very high value samples. For example, this data I'm about to show you is for nanoparticles used in drug delivery, where each batch is very high value, and the customer wants to make sure that all of the samples within size specification. This is a picture of the system installed at a biopharmaceutical plant in Cambridge, Massachusetts. The result you see here above shows mean size on the left in nanometers, and on the right side is homogenizer pressure. So the system was placed downstream of homogenizer. 11 measurements were made, and in the first study, the customer wanted to understand the relationship between homogenizer pressure and generated particle size. And what we see here, as the pressure increases, the size distribution decreases. Once the customer understands what is the optimum pressure, in this case, the customer wanted to generate particles right at 100 nanometers. Then as they start doing batches, you see here at the beginning of this batch, the particles are actually undersized. So they reduced the pressure and then started generating the particles exactly in the size range where desired. So this is a unique capability of being able to take the Nicomp optics and algorithm and apply it to online measurements. The system can also be configured to measure zeta potential, which is a measure of the charge on the surface of particles. This is an easy measurement to make. The way we do it is we take a plastic disposable cell, fill it 3/4 with the sample, insert our dip cell, and then these electrodes are going to apply the electric field, and we take the measurement right here. We're going to measure the motion of the particles either using frequency or phase shifts. Actually, the phase analysis light scattering, the PALS, is more sensitive, so that's how I do all of my measurements. We apply electric field, we use PALS, and we can convert the mobility of the particles to the zeta potential. Typically when I'm doing zeta potential, I'll take multiple measurements, take the average. Like anything else in particle size, it has to be repeatable to be believable. These dip cells are actually the less expensive way to take the measurement compared to disposable cells, because this dip cell will last you for thousands of measurements over many years. We can work at much lower voltages, a smaller applied electric field, because we're actually taking this measurement directly in between the electrodes. It's also very, very beneficial when measuring biological samples, because then we reduce the joule heating and we don't have to worry about baking the sample onto the electrode. It's also better at high salt concentrations. This graph shows a setup for the measurement. All we really do is we fix the temperature. We choose the electric field strength and then choose, most of the time, the Smolakowski limit as opposed to Huckel to define the kappa A ratio. To make a zeta potential measurement, add the sample to the cuvette, insert the dip cell, wipe off any liquid from the surface, attach the zeta potential cable, insert into the cell holder, hit go, and start the measurement. This is data from a high salt concentration sample. This is a lipid fat emulsion. We started at very low salt concentrations where the zeta potential is down here near -50. Then as we increase the salt concentration, we actually see a decrease in the zeta potential and then a charge reversal, which is what typically has been seen and has been published for this particular sample. So in the end, we end up at a positive 4.8 millivolts, and this measurement was made at 0.9% salt concentration. There's a lot of benefit to measuring this because 0.9% salt concentration is essentially physiological saline. And if this sample is to be injected into humans, lots of people want to do these measurements at high salt concentration. And the dip cell is a better way to do that because the salt doesn't build up on the electrodes, they're easier to clean, and much less expensive to perform these kinds of measurements. The next zeta potential result I'll show you is an isoelectric point determination. The isoelectric point is the determination of at what pH do we reach a zeta potential of 0. This is a sample that I started titrating. I was just titrating by hand. It started at a pH 6.7. I was adding acid to reduce it down to a pH below 4. And as you can see from the data here, we go through this line and we reach the isoelectric point at about 4.26. The table on the left shows how repeatable these zeta potential measurements were made. And this whole measurement took me not even an hour. So a very nice tool for doing isoelectric point tests, which can be useful to determine the surface properties of complex particles. In conclusion, the Nicomp is a very flexible system. You can just buy the standard configuration for a broad range of samples, or you could customize it to your specific application. The Nicomp algorithm provides the highest resolution when measuring complex multimodal samples. The system includes unique accessories such as auto-dilution, the auto-sampler. Most zeta potential data is taken using phase analysis light scattering, a very sensitive technique using our unique dip cells, which is an inexpensive, very accurate way to take very many zeta potential applications. People choose the Nicomp mostly because of the data it generates. It's high accuracy, it's high resolution, it's easy to use, and it's inexpensive to operate when doing many zeta potential measurements. I recommend you visit our website to download application notes and technical notes to get more information about the Nicomp DLS system.